Let's look at a case of how to calculate magnetic force between two current-carrying conductors such as this one. What you have here is you have a long wire on the left carrying a current, let's say I1 in the direction shown, and you also have a rectangular loop carrying current in that direction. Let's call the strength of the current I2 ampere. Now we can assume that the distances is A, that distance is B, and that length of that loop is C. We know that this current I1 will produce magnetic field at all the positions where the loop is. So you should be able to calculate the magnetic force experienced by this loop, and that is what we want to determine. So let's put in some numbers based on the setup. So this long straight wire carries a current 10 ampere. The rectangular loop carries a current of 5 ampere in the direction shown. We want to determine the direction and magnitude of the net force exerted on the loop by the magnetic field of that long wire. These are the distances. One of the sides is 20 cm long for the loop. The distance between the sides of the loop from the long wire is 10 cm and 1 cm. So in order to determine the amount of force that this wire exerts on this loop, we need to consider the effects piece by piece. First of all, we need to divide up the loop into segments. So let's assume this segment is segment 1, this is segment 2, that's segment 3, and that is segment 4. We analyze the force exerted by this long wire on these segments individually and then just add them up to get the net force. So that is the strategy. Let's begin with segment 3, that is horizontal segment right there. We note that throughout this length of segment 3, the magnetic field produced by this wire varies because the distance varies. So let's take an arbitrary element on the side 3, say that element, a current element, the length of which is, let's say, dr, so a very small element, and it is situated at a distance, say, r from the long wire. So the center of that little element is situated to distance r from the long wire. The magnetic field produced by the long wire at the center of that tiny element will look like this. So that is the direction of the magnetic field, and exactly where the element is, the magnetic field will go into the board. So we represent that with a cross. The force on that tiny element, let's call it dF, situated on side 3 of that loop, is given by the current in that loop, which is 5 ampere, the length of that element, which is dr, and the magnetic field as that element, that is given by mu naught, the current in this long wire, which is 10 ampere, over 2 pi, the distance between that element and the long wire, which is quite simply r. Note, I have simply used the fact that the magnetic force on a current sitting in an external magnetic field is given by that expression. So to determine the total force on this length 3 that covers the entire length, we need to integrate this expression. So integrating that, you get the total force on side 3, and the right hand side taking out all the constants, 5 mu naught 10 over 2 pi, and integrate over 1 over r with respect to r. Now note the limit of integration. If the element is here the value of R is 1 cm. And if the element is on the other side, the length is 10 cm. The value of R, that is 10 cm. So the integration limit goes from 1 to 10. Now you note that you don't have to change the units because it will appear as ratio. So to calculate the magnitude, it is quite simply 50 mu naught over 2 pi natural log, that's what you get by integrating 1 over R, 10 over 1. The direction of this force is, the magnetic field is going into the board. The current is going, the 5 ampere current is going that way. So by using the right hand rule, the direction of this F3 force is upward. So this side of the loop will experience a force in an upward direction. So F3 is upward with that much magnitude. Now we can use the same reasoning to compute the force over this length 4. So creating an arbitrary element with length, let's say dr, and the distance from the long wire being r, the expression for the force on that side 4 is again given by a similar integral that again extends from a minimum value of r of 1 cm, that is when the element is here, and to a maximum distance of 10 cm when the element is there. So the limits again goes from 1 to 10 cm, integrated over 50 mu naught over 2 pi dr over r, which will give you exactly the same expression as before, 50 mu naught over 2 pi natural log of 10. The magnetic field created by this current along that side will be again going into the plane. So if the magnetic field is going into the plane and the current is going to the left, the direction of that force F4, according to the right-hand rule, will be going downward, opposite to that of F3. So the direction of F4 is going downward. So you immediately see F3 and F4 cancels each other. They have the same magnitude, but opposite directions. That will leave us with only two sides, 1 and 2. So let's look at side 1. The magnetic field from current 10 ampere acts like that, and at side 1 it is going again into the board. Magnetic force experienced by side 1 is given by the following. 5 ampere, that is the current on side 1. The length of side 1 is 20 cm, so let's convert that into meter. The magnetic field at side 1 is given by mu naught. The current is 10 ampere that produces that magnetic field at side 1 over 2 pi, and the distance is quite simply just 1 cm. Converting that into meter, 0.01 meter. Note that for side 1, the current is going upward, the magnetic field is going into the board, so the direction of force will be leftward. So that is the direction of F1, leftward. Finally, side 2, that's that side right there. Note the magnetic field, due to current 10 amperes, going like that. And at side 2, it's going into the board again. The magnitude of it, it's given by the current is 5 ampere. The length of side 2 is 0.2 meter. The magnetic field at side 2 is mu naught 10 ampere, that's the current producing this magnetic field, over 2 pi. The entire distance from here to here is 10 cm, so that is 0.1 meter. Note that along side 2, the current is going downward, the field is into the board, so the magnetic force is going rightward. So this F2 has a direction rightward. So now the net force can be obtained by adding F1 and F2. The magnitude of F1 will turn out to be 2 times 10 to the power minus 4 newtons. The direction is leftward. And the magnitude of F2 is 2 times 10 to the power minus 5 newtons, and the direction is rightward. So the net force, which is obtained by adding F1 and F2, it's a vector sum, will give you an answer of 1.8 times 10 to the power minus 4 newtons with a leftward direction. And that solves the problem. Thank you for watching.